All right, let's take a look inside one of the most important inventions in, well, human history. It powers just about every part of our modern lives, but you probably almost never even think about it. Today, we're diving into the electric motor. And I'm serious, just think about your day so far. The fan that's cooling you down, the washing machine cleaning your clothes, that blender in your kitchen, and yeah, even the electric car you might be driving. They are all powered by this one incredible device. They're like the invisible workhorses of our entire world. So what is an electric motor, really? At its heart, it's a converter. It takes electrical energy, the stuff flowing from a battery or an outlet, and magically transforms it into physical movement, into spin, into work. It's that simple, and yet it's that profound. But how on earth does it actually do it? Okay, to really get how a motor works, we have to start with this fundamental dance between two invisible forces, electricity and magnetism. This is where the real magic happens. Here it is. This is the single most important principle behind every single electric motor out there. If you take a wire, pass an electric current through it, and stick it inside a magnetic field, that wire gets pushed. It actually moves. This amazing phenomenon is called the motor effect, and it's the secret sauce to everything we're talking about today. That's the million-dollar question, right? I mean, if you're going to build a machine, you absolutely need to know which way the parts are going to move. Is it up, down, left, right? Well, luckily for us, there's a super handy tool for figuring that out. It's called Fleming's left-hand rule. And you can do this with me. Hold up your left hand and make your thumb, your first finger, and your second finger all point out at 90-degree angles to each other. Got it? Okay, your first finger points in the direction of the magnetic field. Your second finger points in the direction of the current. And that means your thumb, well, that points in the direction of the force or the motion. It's a fantastic little trick for remembering how these three things relate. And of course, physics has an equation for this. To get the biggest possible push, you want the wire and the magnetic field to be at a perfect 90-degree angle. And when they are, the formula is beautifully simple. Force equals B times I times L. It really just comes down to how strong the magnet is, that's B, how much current you're pushing through, that's I, and how long the wire is, that's L. The main takeaway here, a stronger magnet or more current means a much stronger push. So, now we've got a push. But let's be honest, a single push isn't all that useful. What we really want is continuous rotation. So how do we get from a simple force to a non-stop spinning machine? Now, this is where things get really clever. Instead of just a straight wire, you make it a loop. The current flows one way on one side of the loop, and then it flows the opposite way on the other side. So, what does our left-hand rule tell us? It means one side of the loop gets pushed up, while the other side gets pushed down. And just like that, you've created a turning force, what we call torque, that makes the whole loop want to spin. To keep that spin going, you need a few key players, all working together. You've got your power source, obviously. You've got your coil of wire, which we call an armature, and the magnet that creates the field. But the real unsung hero here is something called the commutator. Think of it as a clever little reversing switch. It's a split ring that flips the current's direction every single half turn. Why? So the forces keep pushing the coil around and around in the same direction. That's the secret to continuous spin. So there we have it, a machine that turns electricity into motion. Pretty cool. Case closed, right? Well, not quite. There's a much deeper, a much more elegant principle at play here. It's like a secret identity, hidden inside every single electric motor ever made. So what is this big secret identity? Well, it turns out the very same physics that lets a motor work has a fascinating flip side. To figure it out, all you have to do is ask, what happens if you spin a motor by hand? And here it is, the big reveal. A motor and a generator are the exact same machine. I'm not kidding, they're mechanically identical. If you put electricity in, you get motion out, and we call that a motor. But if you put motion in, if you physically turn the shaft yourself, you get electricity out, and we call that a generator. They are literally two sides of the very same coin. So get this. While your motor is spinning away using electricity to create motion, it is also acting as a tiny generator at the exact same time. The spinning coil naturally creates its own voltage. You can picture it like a headwind blowing against the electricity that's trying to power it. This self-generated voltage has a name. It's called back EMF, or electromotive force, and it literally pushes back against the power source. Now, this ghostly voltage pushing back sounds like it would be a bad thing, right? Like some kind of inefficiency. But actually, It's the absolute key to how motors work so well. Let's dig into why this secret identity matters so much. You see, back EMF isn't a bug, it's a feature. It's the motor's superpower. Because it pushes against the incoming current, it becomes a perfect automatic regulator. When a motor is just starting up, it's spinning slow, so there's almost no back EMF. That means it can draw a ton of current to get going. But as it speeds up, the back EMF gets stronger and stronger, pushing back more and causing the current to naturally drop. It's this elegant, built-in self-regulation that keeps most motors from just burning themselves out. And so we're left with this absolutely beautiful symmetry sitting at the heart of our entire modern world. The machine that we use to move things is, by its very nature, the same machine that creates power. It's a perfect reflection of the laws of energy conversion. So you have to wonder, what does this deep connection between motion and electricity, hidden inside the most common machine on Earth, tell us about all the other invisible forces and potential just waiting for us to tap into?